All right, so this is the pre-lab that goes with lab 6, the randomization lab, which is about hypothesis testing. As always, I've sent out the R Markdown document via Canvas, and you'd need to download it onto your computer and then upload it to RStudio Cloud. I'm working locally because I can make the font size a little bit bigger, but all the code should work the same on RStudio Cloud. And we're just going to start by loading our packages like always. So I'm going to library tidyverse and library infer, and then I could click the play button to run that. And then we're going to use my example data set that I'm always using. And I would say to make our lives easier, let's just drop the NA values for these two variables we're going to be talking about today. It's going to drop down the size of our data set, but it's just going to make our lives easier. So this lab is about hypothesizing and performing hypothesis tests. We're going to look at the relationship between whether someone is self-employed or not and the number of hours they worked last week. And we might want to know if there's a significant difference between those two groups. So let's compute our observed sample statistic. I'm going to do GSS, and then I'm going to group by my categorical variable, self-emp, or works for somebody. And then I'm going to do a summarize, and I'm going to say mean is equal to the mean of number of hours worked last week. And then if I control enter here, I can see that it's 38.9 versus 41.6. And those means look different to me, but we need to do statistics to actually say if it's significantly different or not. So the first step to do a hypothesis test is to state your hypotheses. We can write them out in R Markdown using either words or notation. We can use this thing called LaTeX or LaTeX. It's not latex, but this is a way to write mathematical notation. If you want these big equations, you put $2 signs at the top and 2 at the bottom, and then you can do things like H and then an underscore and a 0, and that'll make H with a subscript 0, and then /mu underscore, and then all this stuff in curly braces will get put as a subscript. And I made this text so that it would look a little bit nicer. If I took that off, it kind of gets all mushed together. So I'm going to put that back. Text, curly braces, and then close the curly braces. But if you don't want to mess with that, you could also have just written it out in words. So our null hypothesis, that's the boring thing. This would be that there would be no difference in average number of hours worked by people in the self-employed and someone else categories. And the alternative hypothesis, that's the interesting thing that we're kind of secretly hoping will be true, that there is a difference in the average number of hours. And we're going to use randomization to see what the world would look like if the null hypothesis were true. So we're going to try and ensure that there's no relationship between these two variables by breaking the relationship and mixing up one of the variables. I've got a YouTube video that I made for my lecture, and it has some connections between Bootstrap and randomization distributions if you want to think more about this. So we're going to use the same kind of data pipeline that we did for the Bootstrap to help us with this. So I'm going to make this new thing called Randomization, and that's going to get with the assignment operator GSS then, and I need to specify an explanatory and a response variable. My response is the number of hours worked last week, and my explanatory variable is whether they're self-employed or not. Then I add in this new step, which is I hypothesize, and my null hypothesis is that these two variables are independent from one another. And then I'm going to generate one rep of type equal permute. So if I question mark generate, I can see that there are some different ways that I could generate things. I could do a bootstrap, a permute, or a simulate, and I'm going to permute. So I'm going to just mix up the values of one of the variables. So if I run this chunk of code, nothing happens in the console, but I do get something new in my environment. And this is a data set that has 1,381 observations, so the same number of observations as my original data set of 3 variables. So it has the number of hours worked last week, that's the way that it was in the original data, and then I've mixed up the self-emp or works for somebody, and then I've got this replicate column. It's going to be 1 here because we've just done 1 replicate. So it has 1381 observations. The the same number as our original data set, and just 3 variables, the 2 we are interested in, plus the replicate. And we could also do grouped means here. So instead of starting with GSS, we start with one randomization, then group by and summarize. And if I run this code, I can see, well, these means don't look that different. 40.8 versus 41.3. I think that could just be the result of chance. And actually, it is the result of chance. We ensured that by permuting one of the variables. Because the permutations are random, they're going to look different every time. It means that we need to set a seed. So I'm going to Control Enter here, and I could go move this up to the top of my document and put it in my setup chunk to make sure that it happened up there. You really only need it in one spot. And if you don't remember about the seed, you could go look at the Bootstrap video from last week. So now just having that one randomization sample, it's not that interesting. If we want to make a distribution, we need to do that a bunch of times. Usually we do it at least 1,000 times. I think for the real lab, it asks you to do it 5,000 times. And in order to avoid saving a ton of data sets, we're going to add another verb to our pipeline, the calculate verb. So I'm going to make a new object called randomization. This is going to get GSS, then specify the response, an explanatory variable, then hypothesize, the null is independence, then generate, and now I've changed this. Before I just had reps equal 1, now I'm going to do 1,000 reps, but still of type permute. And then I've added one more thing on here. I'm going to calculate, and my stat is a difference in means, and then I need to tell it what order to do that subtraction. So I'm going to do self-employed minus someone else. So if I run this code chunk, it's going to take a second because it has to do it 1,000 times, but then it shows up in my environment. And this data set has 1,000 observations just of 2 variables. So it has replicate, so this is for my first randomization sample, and the difference of means, and then another difference of means, etc. So the first time, self-employed minus someone else, the self-employed people were working 0.88 hours more, then 1.69 hours less, 0.14 hours more, etc. So this has 1,000 variables, 1,000 observations, the same as the number of samples we took, and 2 variables, replicate and the randomization statistic. And then what we're actually interested in is the distribution of that statistic. So let's go remember what it's called. It's called stat, and let's make a histogram of it. So I'm going to do a ggplot of that randomization data set plus a geom histogram with an AES x is equal to stat, and then I can Control Enter. And this distribution is symmetric and bell-shaped, which makes sense because sampling distributions usually are shaped like that. So even though the distribution of a sample might be skewed, once you make a sampling distribution, where you take a sample and you compute a statistic and you record it and you do that process many, many times, your sampling distribution is usually pretty symmetric. And then we might be interested about the mean of that distribution. So I could take my randomization data and then I could summarize the mean is equal to the mean of that stat. And it is negative 0.0217, which is almost 0. So you might have gotten a different number. In fact, you probably did because you probably set a different seed than me, but I would guess that it's about 0. Does that make sense? Yes, because randomization distributions are always centered around the null value, which is 0 in this case. Great. But then the thing that we really want to do with a randomization distribution is find evidence for or against the null hypothesis. And we could just use the 95% rule to kind of eyeball, what are the most common values. I'd probably say, negative 2.5 to 2.5. So any observed statistic that was more extreme than those values would be pretty weird to see. So let's try and remember our observed statistic. That was GSS, and then we grouped by self-emp or works for somebody, and then we summarized mean was equal to the mean of number of hours worked last week. And so the difference between that was this minus that. So it was like negative 2.7. Actually, did we do the subtraction the other way? Which one did I say? Self-employed minus someone else. Okay, I did it correctly. Good. We think it's pretty weird. That would be kind of out in the tails, but we'd really like a specific p-value for how much of the distribution is as extreme or more extreme. And there's this function get p-value that'll help us with that. So let's take our randomization distribution and let's stick it into get underscore p underscore value. And what I need to tell it is what my observed statistic is, in this case, negative 2.7. And then I need to tell it the direction. And in this case, we're going to do both because it's a two-sided hypothesis. Let's control enter. And there's my p-value. So p-value is 0.022. So what we conclude at the alpha equals 0.05 level, we reject the null hypothesis because I'm going to use a little more inline LaTeX here. So I'm going to do a $. 0.022 is less than 0.05. Close it off with another $. And then we could also do the conclusion in context. We have evidence to suggest that there is a difference in the mean number of hours worked between self-employed and not self-employed people. And then the question is, how would this change if we were doing a one-sided test? Well, the p-value would get smaller, and we could actually copy this chunk of code and we could try it again just to make sure that we're correct. So instead of doing direction both, I'm going to do direction, and I'm just going to do to the left. Control enter, and yeah, my p-value is half as big. So the p-value would be smaller, so we would have stronger evidence against the null.